Here's our KDTree. So we are going to start at the root node. Some things to note about this recursion. Because our tree is represented by an array, a convenient thing to do to mark where we are in this array is to have two pointers, or two indices into the array. Lower and upper. Here they're labeled L and U. Lower marks the lowest most index we are currently considering. Upper here marks one past the uppermost index we are considering. I personally like using one past the uppermost index we are considering. Many people use the actual upper index we are considering, so upper would be pointing here instead of where it is over here. That's just up to you to decide. It's convention, or whichever you like better, whichever works out better math-wise for you. Our median is defined as, with my definition of upper here, our median is defined as L plus U minus 1 divided by 2. So that gives our median at 5, 4. So this is 5, 4 is the left of the two middle nodes we have here. So these two lower and upper pointers, or indices, into our array, starting at 0 and here's 6, show that we are currently at median 2 as our node, and that node 2 has this entire subtree underneath it. Okay, so we are going to check 6, 3, our target point. 6, we are looking in the x dimension right now, is greater than 5, so we are going to go to the right. So now we are in our right subtree. To do that, our lower pointer has been updated to point to our new lowest bound, and now our median is 7, 2. Now 3 is greater than 2 in the y dimension that we are looking in, so we will go once again to the right. Now that we are at 9, 6, we are at a leaf node. We can check this because here L and U differ by only 1. If you use the alternative definition of upper, L and U would be the same, or possibly less. So here, now that we're at a leaf, our best point is 9, 6, and that distance is 18. Or the distance squared from 6, 3 is 18. That's 9 minus 6 is 3, 6 minus 3 is 3, 3 squared plus 3 squared gives us the distance squared of 18. Now we come out of that recursive call, and we are back at node 7, 2. So this isn't going back, this isn't calling another function to go back to the tree. This is just exiting our recursive call. Now we are once again in our recursive call for 7, 2. Now we check, this is part 2, we check is 7, 2 closer to 6, 3 than our current best 9, 6 is. 7, 2 has a distance of 1 plus 1. 1 squared plus 1 squared is distance squared of 2. That is much better than our distance squared of 18, so 7, 2 becomes our new best point. Then we check, could there possibly be a node in the left subtree that is closer to 6, 3 than 7, 2 is? We check this by seeing, is the difference in the y dimensions, 3 and 2, that distance squared is 1. That distance squared is less than our current distance squared between our target and our best node. Therefore, there could actually be a node in this left subtree. So we are going to go down into the left subtree and check that recursively. In our recursive call to 8, 1, we are at a leaf node. We check, is this leaf node better than the current best? 8, 1 has a distance of 2 squared plus 2 squared is a square distance of 8 from 6, 3. So that means that no, that is not a better node. And since there are no children, we are done here. We exit this call. And we once again return to our function call of 7, 2. 7, 2 has now checked the target side, and it has checked affecting the current node, and it has checked the other side since that was applicable. So we are done with this recursive call. We go back up to our root node 5, 4. Now we check, is 5, 4 closer to 6, 3 than our best point 7, 2 is? 5, 4 has a distance of 1 squared plus 1 squared equals a square distance of 2. That is the same as our current best distance, so we're just going to leave our best point where it is. We're not going to change anything. Now we're going to check, could there possibly be a better node in the left subtree? And this may not have been the best example, because once again here, the x distance is 5 and 6, gives the distance squared of 1, so there could be a better node in the left subtree. If, for example, this hadn't been 5, 4, but it had been 1, 4, then we would have had a distance squared of 5 squared plus 1 squared is 26, and we would not have to go down into the left subtree. It is this fact that you don't always have to go down to the left subtree that makes the KDTree much more efficient than simply scanning through the list to find the closest node. So we go down to the left subtree. We're at 2, 3. Once again, we're just looking for the leaf closest to 6, 3. So in the y dimension, 3 and 3 compare the same. I'm just going to go to the right. I'm going to say if they're the same, go to the right. So we go to the right node, check 4, 7. Is 4, 7 better than our current best point of 7, 2 compared to 6, 3? 4, 7 is 2 squared plus 4 squared away, 4 plus 16, 20. That is definitely worse than our current distance of 2. Now we go back up to 2, 3. Now we check, is 2, 3 closer to 6, 3 than 7, 2 is? And once again we get the answer is no. It is a distance squared of 16 away. Now we would check here, is there a possibility of a closer node being in the left subtree? So here we'd say the distance in the y dimension is 0, 3 and 3, so once again there would be a possibility. The left subtree, however, is null, so we don't actually have to go down that and traverse that left subtree. At this point we are done with 2, 3, so we exit that recursive call, and we get up to our recursive call once again at 5, 4. Our 5, 4 now has traversed the subtree that contained the target, or that would contain the target. It has checked whether 5, 4 is closer than it, and it has checked whether it needed to go down into the left subtree, to which the answer was yes. So now we have checked all possible parts of the tree that could contain 6, 3, or a close node to 6, 3, and we have ended with the result 7, 2 being the closest point in the tree to 6, 3, with a distance squared of 2. And we are done.